Hello everyone, welcome to In 5 Minutes. Continuing with generation of FM, we are discussing direct methods of FM generation. We have discussed the basic principle and we had seen one particular way in which I can obtain variable capacitance, which is using varactor diode. One shortcoming of using varactor diode is that you cannot get variable capacitance varying over a large range, and hence we need an alternative for variable capacitance. It is available in the form of something called as reactance modulator. So the second method that we are discussing is direct FM generation using reactance modulator. The concept still remains the same. The principle that we use is still the same. You will obtain variable capacitance and connect it across the capacitor of LC oscillator. So the overall capacitor will become C, which is already there, plus the capacitance offered by this new variable capacitor block. Now, before we talk about the overall final circuit, we will discuss reactance modulator a little bit. Because it's a group of components and not a single device, we have to first ensure that it's acting as a capacitor overall. So you can see that the reactance modulator is made up of a variable, a semiconductor device. In this case, we have taken it to be JFET. I can also make it using a device like BJT, for example. You have a capacitor of value C and resistance of value R connected on the gate terminal side of JFET. From the drain and the source, we take out the output terminals. We name them as A and B. So it is looking through the output terminals A and B, we have to prove that the overall circuit acts as a capacitor. So to do that, we will simply calculate the impedance Z, and Z will be nothing but the voltage across A and B, which we are calling V, divided by the current entering through node A, which is called as I. So the analysis that we are going to do, we will have to find the value of the impedance Z, which is V upon I. Now please remember that this V upon I must come out to be equal to minus J into XC equivalent, because any capacitor that we have will offer the impedance in the form minus J XC, where XC is the reactance offered by the capacitor. So somehow we have to prove that looking through terminals A and B, I'm going to see the impedance which is of this form minus J into something. Now that something will become the reactance, and from there we will find out the equivalent capacitance offered by this entire circuit. In this derivation, we will use two important assumptions: that XC is much greater than R, which can be easily done by choosing the value of capacitance to be small enough, because XC is 1 upon omega C. If C is small, XC will be very large. And we need one more assumption which says that ID will be very much large compared to IC, which can also very much be possible given that the first assumption is available, because if XC is very large, that means the equivalent impedance offered by this branch will be very large, and hence automatically IC will be small and a major current will flow in the form of the drain current ID. So with these two assumptions, let us quickly find out the expression for Z.